Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.14. We have gaming optimization, we have TLB optimization, and we have Rust policy coming up. So let's start with the release note, in which Linus explains that there was a delay in the release of the kernel, not because of anything major, but just because he forgot to actually publish it. That's no issue. I won't hold a grudge for making me stay up late last night, not at all, but in any case, we're all happy the kernel is released, but there was nothing major in that last release candidate. So we're all good for the features. So let's start with anti-sync, which is our big gaming optimization. Now, anti-sync we've talked about in the 6.10 release, but let's just refresh our minds a little bit. So anti-sync subsystem is there to kind of emulate the Windows anti-synchronization primitives. Now, synchronization primitive, what that means is pretty much mutexes. Mutex are there to kind of provide a way for a core to say, hey, I'm doing some process here, and all of the other core can look at the mutex in order to know that, let's say, core number 1 is doing a very important task and nobody else can do something while core number 1 is doing something. Well, the mutex is there to say, hey, don't do anything with our program until core number 1 is done. It can be used in a bunch of ways, and it is used a lot throughout any game, of course. So this is very important to have optimized as much as possible. Now, of course, those mutexes needed to be provided to any game that was emulated through Wine, but they were slower than native synchronization primitives, native mutexes that you could use on Linux or that you could use, of course, on your Windows machine, which made game way slower. They made it harder to provide more FPS. So we already know that from the 6.10 release, but what changed? Because on the 6.10, we knew that it was in the kernel, but it was also broken. So what happened here? What changed? Well, they actually solved it. They fixed it. Now it works, and it is amazing. So we see with some games a gain of up to 678%. Yes, that's going from 110 FPS to 860 FPS. Now that's not all games, that's Dirt 3 if you know that game. Anyway, some game will have bigger gains than other. That's just because some games will use those primitives when other games will use other ways of getting their primitives, which will of course change the result. But for those games that heavily uses those synchronization primitives, and if you have a lot of FPS inside of your game already, it's going to make your FPS go even higher, because of course more FPS you have, the more those synchronization primitives are getting used, and the more an optimization will be felt by you. In any case, this is the biggest update for gamers in the kernel since we started reviewing the kernel, so it's really good news, and I'm very happy to see it. Now let's pivot to our second feature. Today we have, well, something that will need a little bit of background in order to understand, because we are going to talk about memory management, about how process go from process A to process B. So let's just start with some clean, quick explanation. First of all, what is the TLB? The translation look-aside buffer. So we have spoken about this a lot lately, so let's just re-explain quickly what it is. When your CPU needs to go and get memory, when it needs to look at a specific chunk of memory, it will need to translate from virtual memory to physical memory. Now, the big difference between the two is that each process will have its own little chunk of virtual memory, which will be mapped to a specific place in your physical memory. But it will, of course, change from one process to another, so each virtual chunk of memory will be different from one process to another, and to see where the virtual memory is mapped to the physical memory, you need the page table. The page table is there to tell you, hey, this chunk of virtual memory is there in physical memory for you to check it. So that makes things workable so that you can have a bigger virtual memory than your actual physical memory, and it brings in a bunch of good things. Now, this page table is pretty slow because it's stored in memory. So CPU makers have made a special place in memory, which is called the translation look-aside buffer, the TLB. So this small place in your CPU is just a place in cache, which will store the last address of your last search. So last time that you went into memory, you asked for this virtual address and it gave you this physical address. So let's just save it into the TLB, or if we need it again, we will be able to, of course, get it faster because it's inside of the CPU. So this is very important to understand, that this is flushed each time we switch from process to process. Because if we go from process A to process B, unless they are part of the same process, which means it's a multi-core process, but if it's a different process, they will need to flush the TLB because your virtual memory is not the same from one to another. We don't want to mix things up. We need to flush the TLB. So now that's understood, let's go into the little story where we have a Linux dev called Rick Van Riel, which works for Meta, that saw that in one of their web server, there was a significant portion of the CPU time that was within the switch IRQS off function. I'm going to call it switch for purposes of this video. Now this is weird because those functions are supposed to be very, very, very fast. I mean, it's functions that are called each and every time you want to switch a process of a core. So switch is really just there to tell the process to go off the core. So this is called a lot of time. So let's just go through the standard process of that command, how it works to go from process A being on the core to process B being on the core, just so we understand what we're working with here. So first of all, we call the switch function. After that, it's going to start the process to remove, of course, the process from the CPU. To start that process, it will clear what we call the CPU mask. Each process in Linux has a CPU mask. That CPU mask tells everybody, hey, this process is working on this CPU and this CPU. So let's say that you have a multi-core process, it will have a CPU mask with one on each CPU that it is running from on your machine. So that way we know with the CPU mask where your process is running. So this needs to be, of course, updated. It needs to be cleared once we are jumping the process off of the core. So again, we do switch it clears the CPU mask related to the CPU core that we're in right now. And after that, it flushes the TLB and let the other process do its thing. So this is the simplified version of how we switch a process on Linux. So this is actually not really good. The reason why it's not that good is because the CPU mask, when you clear it, that's something that you need to wait on if there's other CPU that needs to do the same thing. It's something that your CPU could have contention on. So let's say that you had a multi-core process, you had, let's say, a 64-core machine, you had 32 core working on some kind of process, and all of those 32 core get the switch function at the same time. Well, at that time, what you see is that you will have 32 cores pretty much waiting on the CPU mask to be cleared from core number 1, then core number 2, and everybody will wait for their turn, which will take a lot of time. Now, the way that you solve that, it turns out, is to put that process at the same time as the TLB flush. So what they've done here is that they've removed that clearing process for the CPU mask from the switch function. Now they've put it at the same time as the TLB flush. What it does in reality is that it will remove a little bit of the contention on that CPU mask, because remember, one CPU mask per process, you've got a multi-core process, they're all going to butt heads in order to get to the CPU mask and do the clearing things. Now that it's on the flush side, it will need to be at the same time as a new process is started, and that can fudge things a little, right? It can make things a little bit less at the same time because it will be cleared, but it will be cleared once another process actually started, which can be a little bit less crowded. So that way, they actually optimize the process of clearing the CPU mask, thus making a TLB flush faster. At the same time, they also made a quick optimization by removing some code that was there to declare an error that was pretty much never declared. So they have removed that and only put it for non-production version. So they've hidden it behind an option in your configs. So that's all great. What we see is that simple change can get pretty big results. So if you do a benchmark with ACKbench that's pretty much made to simulate switching process through cores, we see that we have a runtime that passed from 4.5 seconds to 4.2 seconds. So it's a pretty big optimization, not as big as NT-Sync, but still a pretty big optimization for such a small switch. Now let's talk about another big item, which is Rust. So Rust, of course, has been the places for all the debate on the Linux kernel, and we've kind of been thrown in the dark by Linus about it, because Linus pretty much says to us, hey, I want Rust on the kernel, and no maintainer is forced to learn Rust, and that's about it. We didn't know much more than that. Now, there's been a lot of debate, of course, around how we should go about Rust. Should Rust be in the kernel, or should we do that thing, or should we... That's good. There's a lot of channels that likes to make 1500 episode on Rust. I don't really care about that. I care about what's going to affect the code. So that's pretty much what's going to affect the code. Linus came out in a thread that was talking about Rust kernel policy and pretty much says, you're not forced to learn Rust. So that we already know, but how much are you not forced to learn Rust? Because we saw some maintainer that said, hey, I'm not forced to learn Rust, so there's not going to be any Rust inside of my part of Linux. Now, that's kind of insane, and that's what Linus says. So Linus said directly, you cannot do that. You cannot just say, my part of Linux is Rust-free. You can deny to support that Rust code, but you're just going to relinquish your control of that part of the kernel. And when I say relinquish your control, I'm not talking about the control of the C code, I'm talking about the control of the Rust code that is created based on your C code. So as we know, the Rust support on Linux is pretty much carried out by a bunch of bindings. So you bind the Rust code to some part of the C code, and then you can pretty much do the same thing that you would do in C, but through Rust, which has its advantages. So what Linus is telling us here is that a maintainer is not forced to learn Rust, but a maintainer cannot also deny Rust a place inside of its tree. It can only choose, hey, if I want I can learn Rust and actually support that Rust code, or I can say, with hell with it, and I'm not taking care of that code, but I will let somebody else do that support for that Rust code, and I will need to work with those people if ever I do a change. You cannot really do a unilateral change onto your tree that destroys something else for some other people. You can already not do that. Pretty much Linux rules. So right now at least we have the policy, well, it's not really policy, but we have the text of Linus telling us that, hey, that's what I want things to be. So that's a great news for everybody, even if you don't like Rust inside of the kernel, because now we at least know how things should be. Now, of course, I always want to warn people that are a big Rust fan. Rust is a long-term project for Linux. Let's not get crazy over it, because we need to remember that big project in the Linux timetable, we're talking about 10 years, we're talking about 20 years. That's the time that things take to change inside of a big organization like Linux. So if you're expecting everything to be Rust in the next 2 years, you're kind of being ridiculous, right? So please keep in mind that it took, 20 years for a real-time kernel to be a reality, and we're talking about changing the language of the kernel here. So let's stay realistic. This is a great news for everybody, but it's not going to change the full language from one day to another. Now, if we want to talk about positive things regarding Rust, we can talk about the fact that now there's enough binding inside of platform drivers, PCI buses, that devs are saying that they can almost write real drivers in Rust. So people are very happy about it. But we're going to talk a little bit more about Rust a little bit later. Let's go into our last featured change. So now let's talk about FSNotify. Now, FSNotify is already a subsystem in the Linux kernel. It's there to do things once you have some kind of request or some action happen to a file. So of course, then it's a name, FSNotify. Now there is a new event called FS Pre-Access. FS Pre-Access is there to listen to a file, and if an access to that file is done, it will stop whoever is accessing it, and it will prompt another part of the system for data. So you can kind of fill in whatever data you want inside of that file, or you can modify that file, or you can choose however you want to throw data at whoever is accessing the data. Now I find that very interesting because it enables a bunch of ways that you can work around very slow storage, or that you could work around any, well, non-standard storage. So I find that feature very interesting, and I just wanted to highlight it today. So now let's talk about architecture-specific changes, more precisely about x86. On the AMD side, we have their secure encrypted virtualizations feature that has now a new feature added to it, which is called Secure TSC. Now, Secure TSC is there to give the TSC feature, which is the timestamp counter. The timestamp counter is the little count that you have inside of your CPU that counts every time that you have an instruction being run. So if you run one instruction, it will do +1 in the TSC register, which the secure TSC function is there to pretty much say that this cannot be manipulated by the host. So that's very interesting that they again and again add those new features. So another feature that AMD added to their secure encrypted virtualization is segmented RMP. Now, RMP stands for reverse map table. The reverse map table is kind of a permission table that's put in memory that's there to tell the CPU, hey, that part belongs to the hypervisor, or that part belongs to the VM. So that way you can put the permission into memory and make sure that only the hypervisor or a specific VM can access each chunk of memory. This, of course, heightens security because now we have some kind of secure way to make sure that nobody accesses memory that they're not supposed to, that is enforced by the CPU, by the hardware. Now, this was already in the kernel, but the segmented part was not. The goal of the segmented RMP is to do the same thing, but to split it into each NUMA node that you have inside of your system. Now remember, NUMA, what it means is your CPU itself can be split into smaller and smaller chunks where each CPU and their cache will be together. So if you have, let's say, CPU 1 that's with cache 1, of course it will also always preferred, because they're close together, to work together. So they will be inside of the same NUMA node. So when you split your RMP in segment in each of the NUMA node, you have a faster RMP, which is always great because you want those reads and those writes to be as fast as possible, because we're talking about memory, right? So before that, the RMP needed to be contiguous, needed to be continuous in memory, but now it can be segmented and the proper instructions are implemented inside of the kernel. There is also initial support for the AMD AE for DMA. This is a direct memory access, a DMA controller, which is used with the AMD non-transparent bridge. Now, NTB, as they're called, are devices that are made to connect two computers together so that they can each look at each other's PCI Express. So that way they don't have to cooperate to do so. Now, there's no CPU or documentation that we can look to see how that would work, but it's pretty interesting to see the technology. NTB has been there for a long time, but the AE4 DMA, that's something completely new, and we're kind of waiting to see what's going on with that. We also have AMD XDNA driver support for the Ryzen AI NPU 6. Now, the AI NPU 6, as is in the name, is a neural processing unit. It's an AI core. So we now have everything needed in order to run the AI inside of those AI core that are in some laptops. We also have some decoupling of the legacy Northbridge code, the code that manages memory and PCI Express for AMD. So they have decoupled it from the newer Zen era CPU. So their newer Zen, they're now called Node CPU, have more and more features that requires them to, of course, do things a little bit more fancy that it only works with those new CPU. So splitting the codes make it easier to manage because you don't have to try to make things fit with those legacy CPU. You can just do your own thing pretty much and assume a minimal amount of modernity inside of the CPU that is running the code. We also see some big cryptography gain. So, well, big. It's not as big as we've seen in the past, but we see 2% faster on AES GCM for Zen 4 and Zen 5, and 3% faster on AES XDS for Zen 5. So that's good. That optimization also applies to Intel, but on Intel it's very minor. It's 0.1%, so it's nothing big really. But this is added to the big optimization that we've seen in 6.11. In 6.11, we went up to 162% faster on some algorithm. So it's not as crazy, but it's still interesting to see how they managed to make things even faster. Now, we've talked about faster, but sometimes things need to be more efficient. And here is the big change for efficiency. So they've changed the energy performance preference, the EPP value for Ryzen and EPYC. Now, EPYC is under the performance EPP value. So it will pretty much always run full speed, and it's normal. It's because EPYC are server CPU, right? And Ryzen has now switched over to balanced performance. The reason why they put it on balanced performance while before it was on performance is because if you would just watch a YouTube video on a laptop, it would eat up double the wattage just by changing the performance to balance performance to performance. Anyway, you understand what I mean. Double the wattage for no real gain. It's just that putting it to performance make it put the gas pedal to the metal, so it makes things very, very inefficient. So this is a change that everybody should like. We like having pretty much the same benefit without having the same wattage usage. And we also have one last thing for AMD, the better handling of the AMD preferred core. So AMD preferred core, of course, is one core that pretty much does everything, and while the other core are waiting on the sidelines. So that feature was added in 6.9, and it is now optimized way further. It's always good. Again, that's good for efficiency. Now let's switch over to Intel, which made some change, not as much as AMD in this release, but some change with the ACPI CPPC. Now, we've heard about ACPI CPPC. It was reported on with 6.12, which is used to change the scaling factors for the hardware P state, so for the performance level. So what you could do is you could pass through the ACPI CPPC in order to change the frequency, to change the performance of your hardware, because some hardware could not be directly manipulated by the method that we had before. So more modern laptop like Intel Arrow Lake had this issue. So now we have a better implementation to actually use with those Intel Arrow Lake processor. Those are 2024 processors, so of course brand new, and they needed that in order to have better performance. We also have restructuring of the TDXD Intel Trust Domain Extension code to make way for the new Trusted Execution Environment, the TEE, which is built into modern Xeon CPU. So we see more push, of course, we've seen from AMD into confidential computing, we see it in ARM, and Intel too takes this very seriously. So we see that they're making some way in order to make sure that they can make their new feature work into their modern Xeon CPU. I also wanted to mention PowerPC, which has gained the lazy preemption support, which is of course always good to see those new features making their way into every architecture. But for now, let's go into more core kernel features. So let's talk about PID Max, which is a system CTL knob, which is there to set the highest number of process ID that can be generated. So of course, if there is a maximum limit to the number of process IDs, that means that there's a maximum limit of process on your system. Now, this process was already very high, and what they wanted to do is to make it so that PID max is now tied to a PID namespace. Now, PID namespace are kind of separate little realms that you can do for yourself for processes. They are extensively used into containers. So if you have a container, it will have its own PID namespace, which will kind of separate it from all of the other processes that are running on your machine. Now, the issue was that if you just had a PID max that was too high, you had some old software that would not be able to handle it. One example would be the Android's implementation of libc, Bionic, which in 32-bit could just not survive a PID max value that is greater than 65,535. So if you put it any higher than that, it would just die. So if you wanted it to work on your system, you needed to limit your whole PID max for your whole system to that amount, which is ridiculous. Let's say it how it is. So making it separate, making it per PID namespace, make it possible to put all of this into a container, put it all under some PID namespace, and then you can change the PID max independently. We also have the madv don't need and the madv free operation in madvice that will now delete automatically the page table entry that are related to the memory that they're working on. So you can use those commands in order to say, hey, I don't need that memory anymore, but the page table entry could sometimes just stay there and waste memory. So in some case, of course, just to make sure that everybody understands, page table entries are part of the page table. At the very start, when we were talking about the TLB goes and look into the page table when it doesn't know where things are, and it picks up entries from there in order to know where things are. So page table entries are just part of memory that points to a physical place in real physical memory. So those page table entries, those PTEs as we call it, can take place in some application. You have some program that will create a bunch of them and then delete a bunch of them. So when you do that, if you don't actually delete the PTE, but just say that you don't need the memory anymore and the PTE stays there, well, you can have your memory filling up with a bunch of things that you don't need. So it's really important for you to delete it. That's why it's been added into this release. We also see that C groups can now regulate the memory found in a GPU. So Intel has put some quick things into their driver that you can now, of course, control with C groups, the allocation of graphical memory inside of the GPU. Don't know how useful that is, but that's pretty funny. If you don't know, C groups are there to give kind of permission and quotas and those bunch of things for a given place in memory, for some files. So it's there to manage how you use something. They're also called control groups. So applying them to GPU memory is very funny in that case. Now let's talk a little bit about file system, and let me just start with bcachefs. But we're not going to talk about any features today. The reason why I don't want to talk about features is because, well, there's something new. There's a new fresh wind of fresh air, let's say it that way. We have not seen Kent Overstreet, the creator of bcachefs, do any dumb things in this release. So let's celebrate it, everybody. Okay, let's take this time to be very happy. Turns out that when you apply the rules, because if you remember in release 6.13, he got banned from that release for, of course, violating the code of conduct. Turns out, when you apply the rules, you get people that follow the rules. Who would have known? So now let's talk about BTRFS, which made a quick change. Turns out BTRFS, when it wanted to read from a RAID 1, it would look at a PID of the reading process to make its decision on where it would read. So do I read on the first disk, the second disk, or let's say that I have a bigger RAID, do I read on the fifth disk of my RAID 1? Well, how do I choose the PID? Well, what happened if the PID of the reading process is the same because there's only one process reading? Well, we're only reading with one drive. So that was not a good idea. So now they have added a new round-robin algorithm in order to do some read balancing. Or you can also say, hey, always read from that drive. So it can make things a little bit more balanced and little bit more logical, right? Because you don't want to only read from one drive. And I kind of assumed that RAID 1 would give you some performance bonus from being RAID 1, right? From having all those drives, having the same thing, it should read pretty fast. I'm kind of surprised that that was not implemented by default. Now let's talk about XFS, which has added some change to their real-time device mode, which is a special mode that's there to try to get consistent and predictable latency from file system operation. So they now have support for their reverse mapping. Now reverse mapping are kind of a backup of the extent. So you keep a copy of your extent. The extent is how big your chunk of data is, and in XFS it also contains some permission of that file, so the ownership of that file is inside of the extent. In any case, you have a copy of that extent at the same place as the place that you keep data. So that way it enables a bunch of other features. It enables reflink, which is sharing blocks between files, and it enables other feature. It's kind of a treasure trove of feature that you enable from just that feature. But for now, we have reverse mapping, and we also have reflink, like I said, sharing blocks between file, which is supported inside of the XFS real-time device, which is really good to see. XFS always making moves toward the future. I mean, is there something that XFS cannot do at this point? I'm sure it can cook you the dinner. It probably can do everything. Now on the NFS side, we see support for the NFS 4.2 Plus attribute delegation. Now, to be completely honest, I don't really have a clue what it does that much. I know that the client side was added, for those feature was added in 6.11, and it does better handling of the modification time on the server side. So no clue what it does apart from that, but on the local I/O functionality that we've talked about, there's more work that has been put on it. Now the local I/O functionality is the functionality that manages to look at where does the request for NFS come from, and if it comes from the same machine as the server, it will just switch to another protocol in order to not waste its time trying to communicate like it would over a network. So it will make things way faster. Now let's talk about Fuse a little bit, because Fuse is in a perpetual refreshing pretty much. Everybody wants to rewrite Fuse or either change part of Fuse, because Fuse is a very good thing, right? It's file system in user space. It allows you to have a file system in user space. You don't have to have your big permission and all that. So that's very important, but it's also very, very, very complicated and a convoluted, unoptimized system behind the scene. So we've found a pretty big bottleneck that we've solved by I/O Uring. So I/O Uring is just a way that is used throughout the kernel. So changing some part of Fuse to I/O Uring managed to help performance a lot without rewriting it from the ground up. So of course, that's good news for that. Now let's just talk very quickly about F2FS and OCFS2, which were converted more and more to folios. Remember, folios are a bundle of pages. Pages are the basic block of memory under Linux. So Linux, everything is stored into pages. Pages are normally 4K of memory in your system. You probably need more than 4K of memory for a given task. So what do? You put them in a big folio, and that big folio is easier to manage than simple pages. So when applied correctly, it actually makes things way faster. Now, there was some work also on SquashFS. So SquashFS is a file system used for live CDs or live USB sticks, or pretty much everything that is used live, in order to remove memory that was not used. So the way that they did it is they had an unnecessary cache. So they had a step where they put something in cache, and right after that, read it from the cache. And at the end of the day, the cache was useless. So they just fix that by removing the cache, and now we have a faster, well, probably faster a little bit, but more efficient with memory SquashFS. We also have an improved read speed with the common internet file system CIFFS and the AFS Andrew file system by changing how they do their requests. So both of those are internet file system that pretty much happen over the network, and the way that they do their requests normally is a bunch of small requests for data, and once they receive their data, they package it into memory and then try to work from there. Now it turns out that's not really great because you want to use things like folios in order to have optimization when you transfer bigger and bigger chunk of memory. So let's say that you have a big chunk of memory that you want to request from the other person, from the file system. Well, you would want to be able to put it inside of a big folio instead of having all of those single page or even worse, very small folios that you have to manage. So the way that they did this is instead of just doing a bunch of small requests and then managing them as they come, they did the same small request, but they put what they call a single work item, which is there to manage those requests after when they come back. So when they come back, the work item is there to kind of bundle them all neatly into a big folio where they can then be used for something else. So that makes, of course, an optimization in latency and how the memory is being used. Now we also see a new feature from the statx system call, which can now return the alignment for read operation on a file. Now that's important because some file may need some offset to be written, but some files can also need an offset to be read. So before that, you could only have the write offset. The reason why you split them both like that is because sometimes you have some kind of storage that will have different read and write alignment. So one way to see that working would be some hard drive that would be able to write only 1 megabyte chunks on the drive, but that could be able to read some 4K chunks on the drive. There are some hard drives that actually do this, so for that, having those information can be very important, especially when you manipulate those chunk of data in the most optimized way. Now VFS can cache the symlink length inside the inode in order to speed things up. So VFS, remember, VFS is the layer that's in between your file system and the rest of the Linux system. So when you request some file, first you go look for VFS, and VFS will handle everything from here. Now, if VFS knows that you have a symlink on your system and you've, let's say, read it once, it can cache some of that into its memory. So inside of the copy of the inode that it has inside of VFS, it will cache the symlink length in order to make things faster. How much faster? 1.5% faster. That's pretty good for something that costs nothing, because that symlink length was put inside of a place that is not normally used by symlink, but is still declared by the computer. So the computer will still have that memory laying around even if we don't use it. So that's a great optimization. We also see a revival. We have managed to revive the MD linear device mapper, which is there to glue block device together. So device mapper are kind of overlays that you can put over multiple devices to manage them however you want. Well, multiple. It can be only one device if you want, but mostly multiple device. And you can slap that over them to manage them on a specific way. Now, the MD linear device mapper was removed because it was deprecated, it was unmaintained, and they believed, hey, there's pretty much nobody using it at that point, so let's just unplug it, right? Let's just kill the thing. And turns out there's a bunch of people that were like, hey, I was using that. Why did you do this? So now they have restored it. It was removed in 6.8. It was restored in 6.14. So now it's also marked as stable, which means that even the release that did not have it, so let's say that you have a 6.10, in the next update, you will have that MD linear device mapper in your system. So guess that's all well for the people that were waiting for it. Now let's switch back to Rust a little bit, where we see that the code in the Rust code and the code in the kernel is getting more and more, well, fitting together, right? Because when you have Rust 1.84.0 or later, you will have some more function called the derive coerce pointer, a function that is there to do coercion on a pointer. Coercion is when you change from one type to another. Well, it will be using the Rust implementation of it. So we see more and more of that kind of intertwining of the kernel and the Rust code so that we can just use Rust instead of making our own implementation and then trying to maintain them on our side of things, which is more optimal. Now let's talk again a little bit about AMD, but now AMD GPU, which now support the DRM panic. So DRM panic, we're speaking about it pretty much every release, is the way that you could have a blue screen on Linux. So you know from last video, you have the kind of QR code blue screen that you can have. You can have the of course, something that really looks like a blue screen if you want. There's a bunch of options, but it is now implemented inside of the AMD GPU driver, so you can now have it on your system. And talking about DRM, we have a new DRM boot logger, which is there to throw kernel message on the screen at boot. So when you boot, you have those messages being thrown at the screen. Now, the goal of this system is to be as simple and as universal as possible. So it was made to have something that would work with any DRM driver and would be RT real-time compatible. So this does not take input, that pretty much does nothing else than throwing things on screen, but it works for that. So that's great to see. Now, something that is not that great to see is the Microsoft Copilot key, which is found on new computer. Well, it turns out we now added support for those keys into Linux, because sometimes they use some kind of hack in order to implement them into the laptop, so now we have them compatible with Linux. Now, there's also the Lenovo phone line key that has support, which is funny, but in any case, more support for more keys. Let's be happy about that. We also have the perf tool, which was enhanced a lot in this release, but the most big one, we could say, is the fact that it can now support 4096 cores instead of 2048. It turns out it can be a limiting factor for some people. Who would have known? We also have faster sleep and resume speed. So it turns out inside of the sleep and resume code, there was a bunch of msleep command throughout the code. Now msleep sleeps for a pretty big time in that code, so it's bad because it just makes it wait before actually going to sleep. Now we still need a small sleep time there, and the way to do that is to use the useSleep range function, which itself will often result in smaller sleep. So that passed the resume time from 1.9 second to 1.1 second on a Dell XPS, so that's getting better. We also see a significant reorganization of the code for the CRC32 and the CRC10diff algorithms, which can now be invoked directly from the library interface and no longer needs to be involved in the kernel crypto layer, which makes results simpler and the code more efficient. Also, kernel module will now be signed using the SHA-512 algorithm rather than the SHA-1 by default. Now let's talk a little bit about pages. Now pages are the base of memory on Linux. The bog standard way to store things will be inside of a page. Now the Linux dev are trying to shrink down the pages as much as possible in order to gain speed and memory. So they are making a bunch of changes throughout the system in order to get to that shrinking. One of them was the ability to allocate and free frozen pages that have no meaningful reference count. So those pages that normally would kind of stay stuck there now can be freed and managed by the system, which will make things a bit more efficient. And we also have on the same angle the new ZPDESC memory descriptor, which serve as kind of a page replacement for ZSwap. So ZSwap now uses those kind of page instead of using the standard page. So doing that change again pushes us more and more into a future where pages are smaller. Now that's all for this release. There's been a lot of change in this release, but overall it's been a smaller one. From the words of Linus, he himself says that the changes were not that great. At the start he was kind of worried because there was not as much change as a normal release, but it ended up pretty good. So that's all for today, and I hope you enjoyed. If you did, of course, you can like, you can subscribe, and of course you can put a comment. And I think, is it the first Linux kernel that I'm going to be able to give you a word to put in the comments because it's really fun? So we're going to do CXL, so Compute Express Link. If you put Compute Express link in the comment. We know that you are an absolute unit. Now, if you like this video, of course, you can become a member, which will allow you to see more of my videos and see them faster because you see them before anybody else. So, of course, become a member today. But that's all for today. I hope you enjoyed, and of course, take care.